5. And Chris, go ahead and
Hey,
take it.
all right. Welcome again, listeners, to All Things 3D. Today we have a really great interview here um, with, go ahead and introduce yourself, Scott.
I'm Dr. Scott Klioze. I'm an interventional radiologist here in Daytona Beach, Florida.
Awesome. Well, thanks for being on our program. And Dr. Scott has some unique YouTube videos that Mike has been definitely following with his research into the CAT scan and MRI imaging and conversion to 3D. And so here's Mike showing some of the YouTube footage here for those of us joining on YouTube. And it's some really great research, and he's going to tell us all about it today.
Yes. Well, again, thank you, Scott, for coming on. And like Chris mentioned, I stumbled upon these videos and I found, wow, these are well produced, and they do a very good job, much better than I could stumbling along with it, talking about the technology behind CT and MRIs. And I thought it would be great to have you on and kind of talk about it a little bit more. So it's up to you. I can run these in the background, or I can just go to your camera and you can kind of talk about why you came up with these YouTube videos and what was the direction you were going. Obviously, them being available on YouTube allows a lot of people to look into them and figure out, the technology. And I think it's very important that people understand, the type of radiation that's being used, what the purposes of it, because it's like a black box, and a lot of people only hear what their doctor tells them from the radiologist report. So I thought maybe we could get some more insight from you.
Absolutely. I think that's a very intuitive view to realize that the reason I put this together is for educational purposes. And I'm going to take you back probably almost 20 years. When I was in medical school over at the University of Florida, I got interested in mainly doing teaching venues to explain medically difficult topics. And at the time, I didn't really have any personal knowledge of how to use the then existing technologies to present what I wanted to present. And I remember riding on a plane one day, and I'm coming back from a review course I was going to, and I have one of my radiology books in front of me, and there was a gentleman sitting next to me on the plane, notices what I'm reading, and he looks over and he goes, "Oh, do you do anything with radiology?" And I said, "Yeah." And he goes, "It'd really be interesting to know how that came about, the history of radiology and how that stuff works." And I'm thinking, he's absolutely right. That would be an interesting topic to cover. And the problem is, first of all, a radiologist is a medical doctor. And we all start off going to medical school just like your nephrologist and your family doctor and your surgeon. And then when we go to residency, we all split off and do our subspecialty training. I go into diagnostic and interventional radiology, and my colleagues may go into family practice or OBGYN, whatever. Part and parcel of our training is a bunch of physics. We have to understand the physics of radiation and radiation technology, and that is an onerous topic for a lot of my colleagues. They went into medical school not to study physics and math. Fortunately, I was an electrical engineer before I went to medical school, so
That explains it.
that stuff came natural for me.
Awesome.
So when I started putting these things together, or conceptualizing actually doing 3D imaging, I went to one of the guys at the University of Florida and I said, "Do you know anyone who can do this modeling type stuff? Because I want to present somewhat complex topics, and I really thought at the time that having the ability to show this stuff in a 3D format is going to make a very difficult topic easier to understand." And my first experience was a young guy who was a student over there, and told him what I wanted, and basically it was just a 3D model of a Crookes tube, what we used to generate X-rays, what Röntgen was using when he was doing his research back in 1895. And I just wanted to show an electron going from one side to the other. So he takes about 3 or 4 weeks to come up with this little video, and is so excited. He's got it all done. He calls me over and he wants to show it to me, and it was horrific. I mean, it was really bad. I mean, the thing was black background. There was really no depth to it. The 3D was very primitive, and he charged me $400 for that. So the whole process soured me a little bit. So I kind of learned on my own how to do this 3D modeling. And with the technologies that are out there right now, I think we have such an opportunity to not only advance our understanding of the world around us, but to teach each other things that would have ordinarily been very difficult. The old adage that a picture's worth 1,000 words. I think if you can get a nice 3D animation, that's probably an order of magnitude even more. That's probably
Oh, for
10,000
sure.
words.
Yeah.
So, I mean, it's been a long journey, but a fruitful one, because it makes me happy when I put these things out there, and I can actually see people glean something from my efforts, especially with the MRI video, which we can show in a little bit. But that was a very difficult topic to understand, and having the 3D models makes it a lot easier to comprehend, in my opinion.
Yeah, I agree. I've read several books on the subject of MRIs, but how do you actually put that into words for an audience? I was struggling with. So I thought, well, let's see if I can go out to YouTube and find something, and sure enough, you came up. Now, did I understand correctly that you made your 3D models yourself? These are your
Yeah.
animations? So
Those are my animations. Now, the way I do a lot of these, like the picture you're seeing in front of you, all of the basic primitives, like the ring that you're seeing arcing around the head, and the actual X-ray generator, I can make from basic little primitives. And the head itself, I actually got. There's used to be something called 3D Cafe, where people would
it's still there.
deposit. Oh, is 3D Cafe still available? I couldn't find it. Now I go to Turbo Squid, and people put their models out there in a standard format, and you can download those things and manipulate them. But great repository, and there's so much talent out there. I mean, people do fabulous models, and some of these things you can take in on your own and manipulate them if you know how to do some of the software, like 3D Studio, 3ds Max and stuff like that. But what I was using back then was a defunct program called Raydream Studio. I don't know if you guys remember that or not.
I know of it, yes.
It's a fabulous little program, good introductory 3D modeler that allows you to take primitive structures, basically arrange them into a system that mimicks something familiar, like a CT scanner or an X-ray machine. And you can use different, assign different basically shells on those 3D models and come up with glass and metal, and it's so interesting. I mean, I can only imagine that the mathematics that goes into these programs is so advanced. I mean, you got to take into account how light reflects off of stuff and just transmitted through it. Impressive technology.
Yeah, quite true. And I've worked with some of the mathematics behind it, and glad we have computers, but to do it by hand would take centuries. And nowadays, you can essentially do real-time, what they call photon emission reflectance and transmittive type materials, so that they get super realistic. So, but the fact is that you took the time to do this and create these, these really decent, even though basic models, they really get the point across, and sometimes too much complexity takes away from it. So I think you did an excellent job from that perspective. So hats off to you.
Well, I appreciate it. I appreciate it. Yeah, I mean, like the image you're seeing in front of you, those are all just squares and circles and different extruded elements of a basic geometric shape, and then you can construct them to model. This is Hounsfield's prototype of a CT scanner. The first CT scan looked just like this, and it was a lathe bed scanner. So what a big difference from the thing that you sit in right now and you have your whole body go through.
How did this guy think this up?
It's amazing, Chris. I say the same thing. How did he think this up? But fortunately, he put his effort. He was an early adapter to computer technologies and built the first business computer in London. And after he did that, he took a little time off and he thought about different applications for this computer technology, and fortunately he turned his attention to radiology because he knew that there were limitations to a standard radiographic image, first of all, like we're talking about, it's a 3D body part, and you're trying to image this whole thing and project it onto a 2D sheet of film. So that's where a lot of my training comes into play, interpreting those shadows, and that's basically what a radiograph is. It's a shadow of a three-dimensional object, and you have to be able to figure out in your brain what you're seeing on that 2D image and extrapolate that to the 3D person.
Right.
So Scott, why don't you go ahead and talk about the theory behind CT, and I'll just kind of leave this up, and maybe you can use that as an example there up
Sure.
on the screen. But
I can do that too. Yeah. Okay.
but kind of talk about CT, and then we'll get into MRIs. As you said, MRIs are a little bit more difficult to wrap your head around because you know, you're working with different principles and particle excitation levels that you know, a lot of people without any physics really can't grasp. So maybe you can give us a 5-minute summary, which is probably not enough, but we'll move people in the right direction, and I'll have links to your YouTubes if they want to know more about it. So go ahead and kind of tell us about the basics of CT.
Okay, well, like you see here, this is just the basic prototypes, the second prototype, and this is the object being imaged in the center here. It's the brain. And the idea is to pass X-rays, or an X-ray source, a gamma ray, whatever, from this device here. This is the X-ray generator. It would actually pass through the object and come down here to a point detector. And this is the prototype, of course, so that's all you had was the point detector. And as you would pass that beam through there, you would record the attenuation, basically how many X-rays are blocked as that object is passing through. You would then rotate that object 1 degree, and you would then pass that beam through the object again, and you would complete this all the way around 180 degrees. And of course, you only have to go halfway around because we're dealing with X-rays. So it's not like looking at an automobile where you want to spin it all the way around so you can see all 4 sides. Because the X-rays pass through, you only need to go halfway around, and you get all the information you need. So not only, as in this situation with the car, where you rotate it around and then you can tell everything about that car from the outside, the X-rays passing through the object then give you information on the surface and on the inside. And that allows us to actually see cross sections through the human body. And the CT technology has actually been invaluable in many, many other fields. This is the first image that was obtained with that particular prototype. Very primitive by today's standards, but you can see that you can see where everything lays out there. And Hounsfield wanted to be able to read the print inside of a book. That was his first concept of using X-rays, to be able to look inside a book without opening it up. So kind of an interesting topic. That's actually his lathe bed scanner right there, what you're seeing. This is the second prototype, and it's showing Hounsfield over there to the right talking about his prototype scanner, and these are the objects that he was scanning right there. It's absolutely amazing. And that technology is used in the field of archaeology, where they're getting these sarcophagi, or these the tombs of the pharaohs and the caskets, and instead of having to destroy those by looking inside of them, you can actually run these things through a CT scanner and see what's inside of them non-destructively. So it's got a lot of application in the in the field of history and museum artifacts, so on and so forth.
And I've seen some things like that. So kind of talk about, a lot of people are scared of CTs because they're X-rays, but from what I've been reading, a lot of the new, more modern CT scanners, because of the actual receiving or receptor is much more sensitive, and the algorithms use clean up a lot of the noise. The amount of X-rays that a person is being dosed with is far less than in the previous days. In fact, from what I've read, even less than what you would get from a dental X-ray. Is that true, or?
Well, Mike, you've been doing your research, I see. So that is a big concern now. There's a lot of popular press out there about the radiation exposure, and for good reason. Because the technologies in CT have gotten so advanced, we can see the whole body from head to toe in exquisite three-dimensional detail. And we can do that in less than a minute. You got to understand, this scanner that you're seeing in front of you, this is the first generation scanner, and it had that rotate translate where the X-ray beam kind of slid across in a linear fashion, and then you rotated 180 degrees. It took like 20 minutes to get 2 images. That was it. So you couldn't expose the patient to too much radiation because there were some limits in the machinery itself. So now with our modern scanners, they're helical. You can actually just go around and they slice you up like a big old spiral ham, and we just run the patient in from one side, just like you're seeing here. This is kind of a spiral slice, and as the patient moves through, you're going to see that they well, this is the 3rd generation right here. So that means that, you know, because it was tethered, it goes 180 degrees one direction, 180 degrees in the other direction. And with the modern scanners, you just keep going in one direction. So because we can image more, we get more information, there is more utilization of these CT scanners. And back in let's say 1996, the amount of radiation coming from medical devices was about 15% of your total. And you got to remember that you get X-ray exposures just walking outside. There's X-rays and radiation coming from outer space. There's stuff in some of the solid materials and the gases on the Earth here. You've heard of radon in the basements of the houses up north. So we get some baseline radiation from everything around us. You move forward to 2006, and now you've actually got radiation that is coming from medical devices, accounting for 48% of the total radiation of the population. So you went from 15% to 48%. Half of that 48 is from CT directly. So 24% of all the radiation that we're exposed to is now coming directly from CT. So a lot of stories in the popular press about how much is too much. You got to remember that CT is based on some assumptions, and basically you have some inherent limitations in the electronics of the system. You have to actually model the X-ray generator and the detector and all these things you have to take into consideration. So to deal with the limitations of these devices, you give patients more radiation. So statistically, you average out these imperfections in the system, and that's what allows us to be more precise. So they're coming out with new algorithms, as Mike alluded to, where they're actually modeling some of these statistical quirks in the system. And the first one is called ASER. It's called Adaptive Statistical Iterative Reconstruction. And what that allows you to do is basically expose the patient to less radiation, take into account some of the inherent limitations of the system, and actually still get a nice picture. So we're able to reduce the amount of radiation the patients are getting. The next major step is going to be model-based iterative reconstruction, or MBIR. It exists now, but the problem is it's computationally demanding to a point where one study would take a whole day for the computer to regenerate images. But you can decrease the amount of radiation to the patient by an order of magnitude. So as these technologies progress, we're going to see that we're going to get more and more information with less radiation. So I'm really looking forward to that. So
and
that's on the horizon.
I would assume parallel computing and cloud computing would probably help in improving that performance as well. So yeah, there's lots of things on the horizon. I do have a background in electrical engineering as well, and I've been involved for 30 years in technology. I guess I eat, breathe, sleep it, as Chris would say. I've got every gadget in the world. I haven't found a CT scanner on eBay yet that I can put in my basement, but it's coming.
All right. Well, if I get rid of one from our department here, I'll call you up and see if you're going to be first on my list.
Thanks.
Yeah,
Well,
I would imagine. I just have one quick one. Yeah, and I would imagine, all these like Canon, for instance, they're every year the big step on these cameras now. The most significant breakthrough in the last 5 years that I see in the digital SLR realm is the sensitivity of the chip and its ability to take photographs or video in low light without adding noise. Right?
That's right.
So
And
the
that's exactly what you're talking about, Chris. It's the noise, signal to noise. It's the
right.
same analogy,
So
and
I would
that's what's
imagine these breakthroughs. I mean, I see every year it almost doubles the amount of capability that these chips have to capture an image in low light. I would figure that those same breakthroughs could be shared with this technology. So the ability. So what you're saying is less radiation for the same quality of image.
that is a great analogy. That's exactly right. And what you're trying to do is produce an image with as little light as possible, as little signal as possible. And that's what we're trying to do. The less signal that you need, if you can get rid of the background noise, there's only two things you can do. You can either increase your signal, which means increase your radiation, or decrease your background noise. And that's the idea of decreasing the background noise when you model the inherent irregularities in the electronics, or actually do the model-based iterative reconstruction. So spot
Unbelievable.
on. That's exactly right. It's exciting times.
So
Yeah.
before we get into the MRI portion of this, kind of sum up for us, what is the advantage of CTs? Obviously, MRIs get a lot of the news, but there is still a lot of things that CT scanning can do that MRIs can't. So can you kind of go through the pros on CT before we hit the MRI?
Absolutely. Well, CT is basically the first line of defense in trauma. Patients come in, you're not going to get an MR, and for a couple of reasons. One, there are some limitations to the MR from a physical standpoint. You don't want to put someone in an MR machine who's got metal inside their body that is ferromagnetic, which means it has a magnetic moment. And if you have no history on the patient, if they're trauma, you don't want to be throwing somebody in there with a metal jacketed bullet that comes ripping out of their body. It's a very strong magnetic field. The other problem is you're not going to really be able to see bone very well. So when you're talking about trauma patients, you want to be able to see the bones, the soft tissues, and everything in between. And CT is going to give you a fabulous overview of what's going on with that patient, all the way from the bones to the integrity of the liver, the brain, so on and so forth. So that's going to be the first line of defense, and that's never going to change. We're never going to have MRI as the first imaging sequence that we're going to do on a trauma patient. You'll always see that in CT. As I said previously, the CT is very good for bone. So when patients come in with these very complex fractures, we'll get a CT, and you can actually do the 3D modeling. You got to remember, CT are slices through the body, but now, because we're basically doing volumetric imaging, our you know, guys know what a pixel is, right? A pixel is a picture element. A voxel is a voxel element. So we measure all these little areas on the body by voxels, and we have isotropic voxels now, which means they are the same resolution in the XY plane as the Z plane. So now we have true volumetric imaging. So I can take these axial slices and reconstruct them into coronal, sagittal, 3D volumes. And what's helpful is that you can take that 3D data set from the CT, and you can actually reconstruct like a fractured heel bone, and you can show the orthopedic surgeon exactly where those pieces are, what's separated where, and so on and so forth. As Mike was alluding to earlier, you know, they're starting to do some 3D modeling with body parts. If you got a guy who's got a skull fracture, and you know, let's say it was a really horrible trauma and he has a piece of his skull missing, you could do that CT scan. You could actually fill in that piece that is no longer present, and you could model it. We'd send that information over to Chris, and he could do a 3D printing of that bone shape, and it would basically, on his 3D printer in the background there, pull out a piece of skull that fit perfectly onto that patient's head. So it wouldn't have to be something the surgeon had to trim out and basically mold to that person's defect. Chris would have it ready to go. So that's the exciting stuff coming with CT.
Yeah, and I totally agree with you. And as mentioned, I had a personal reason to do it and printed out a replica of my wife's skull and sent it to her surgeon for them to use for surgical planning, and also did some volumetric renderings that I sent to Johns Hopkins, and they decided not to go with the same type of surgery after seeing these. So there is a lot of potential there, and that's one of the reasons that I'm moving forward and discussing this and making more people aware of it.
Oh, I got to tell you one thing before we move on, Mike. I was at a conference. The Florida Medical Association had their conference over here in Orlando a couple of months back, and they had the students presenting. And one of the sets of students was doing something on inner ear abnormalities. And he was holding in his hand a model of the semicircular canals and the vestibule, all the components of the inner ear. And it was like a beautiful, perfect model. And I said, where did you get that? And he said, I had it made. He goes, you can actually go, and he got MRI data, and he sent it to a company, and maybe something you guys have something to do with. He sent that data to a company, and they printed out a model of the inner ear with the semicircular canals. This thing was beautiful. It fit in the palm of your hand, and he was using it for demonstration purposes to explain his research. So this stuff is here now.
Right. That is just unbelievable.
Totally agree with you, and I have done that, and I've used both MRIs and CTs. So it looks like you may have somebody behind you, and I just switched over to something. So if you've got to take care of that real quick before we move on.
No, we're good. We're gonna.
Okay.
They just needed me to sign some checks, but they'll get those done someplace else. That's all right.
Okay, well, so let's move on to magnetic resonance. As we mentioned, we use X-rays, and we create layers, and then with those layers, we can create models from it. And however, magnetic resonant imaging does not use X-rays. They use magnetic waves or fields. So kind of go into it a little bit, and again, you've got a 25-minute video, and I'm asking you to truncate this to 5. So,
yeah, this is a heady topic, so if anyone's listening and they don't get the concept, don't feel bad, because like I said, this is part and parcel of my training as a radiologist, and I have some of my colleagues, this is the bane of their existence. But Mike's absolutely right. This is a completely different technology. It's not based on the use of X-rays at all. It's based on nuclear magnetic resonance, which you see right here. And NMR was developed in the 30s and